Hey, this is Workbench from Workbench Quagmire, back with day 84 of our Free Code Camp Python certification in 100-ish days. Today we're going to finish up our last theory section here in our graphs module, and then we will get started on our labs and workshops for this module. Reminder, we're done with certification projects, so that's kind of nice. But we do have the big quiz at the end, or the big test to get out of the certification, so to pass the certification. All right, let's get started here. How do priority queues and heaps work? A priority queue is an abstract data type that works similarly to a queue or stack, but with one key difference. As you may already know, standard queues follow a FIFO, or first in, first out approach, where the first element added to the queue is the first one to be removed from the queue. Stacks follow LIFO, or last in, first out approach, where the last element added to the stack is the first one removed from the stack. Queues and stacks only consider the order of insertion of the elements. However, priority queues take the priority of the elements into account. The priority is used to determine which element should be removed next. Usually, the element with the highest priority is removed first, but some implementations may also choose to remove the element with the lowest priority first. This will depend on the requirements of your program. Priority queues are very helpful for practical applications like finding the shortest path between two locations, scheduling tasks in operating systems, simulating traffic, compressing data, and managing networks. In practice, priority queues are commonly implemented, pardon the blue line, I have no idea what's going on here, commonly implemented using a heap data structure. A heap is a tree data structure with a very specific property called a heap property. This property determines the relationship between each node and its children based on the type of heap. There are two primary types of heaps, a max heap and a min heap. The max heap, the value of each node is greater than or equal to one of the nodes of its children, or greater than or equal to the value of its children. In this example, you can see a tree structure with the nodes 8, 7, 5, 2, and 1. Note that the node 7 is greater than the node 2 and node 1, following the heap property. This is true for all the other nodes as well. In contrast, min heap, the value of each node is less than or equal to the value of its children. In this example, we have a node with the value 4, 7, 9, 12, and 15. For example, node 7 is less than nodes 12 and 15, following the heap property. This is also true for all the other nodes. The heap property is key because it ensures the maximum or minimum element, depending on the type of heap, always stays at the top, which makes it very easy to remove. In practice, heaps are typically implemented as arrays to access parent and child nodes efficiently. Using arrays simplifies the logic for accessing these values or nodes because behind the scenes, if the heap maintains the structure of a completed binary tree, the array implementation only requires simple mathematical operations based on their indices to follow where the elements are located in memory. Python has heap queue built-in module that can be used to work with the implementation of min heap. It works by operating directly on Python lists, following specific steps that work with the elements as if the list was a heap, preserving the heap property. To use this module, you just need to import heap queue. Then you need to define an empty list. This is the underlying data structure for the heap, my heap. To add elements to the heap, you call heap push, passing the name of the heap and the element that you want to add as an argument. This will automatically add the element to the list where it should be to preserve the heap property. So heap queue dot heap push my heap, we're pushing the element 9. To get the element with the highest priority, in this case the smallest value, you would call heap pop. Heap queue heap pop my heap combined with the heap push pop combines both operations into one call. This is more efficient when calling them in sequence separately, especially when the heap is large, since it only performs one heapify operation to reorder the list as a heap. Heap queue, heap push pop, heap by heap would push 15, I assume. If you already have a list and you want to transform it into a heap, you can call heapify, passing the list as an argument. Heap queue, heapify my heap. But currently we are sorting the elements by their value, right? What if we want to sort them by their priority instead? You could do this by storing tuples with the structure priority and then element. Since tuples are compared element by element from left to right, the priority will be compared first and then the decision will be made based on them. Please note that in this case, lower values will represent higher priorities. This means that a tuple with a priority of 1 will be higher priority than a tuple with a priority of 3. My heap push pop, or my heap queue push, heap push, my heap, and then we're pushing these tuples. If you need the elements with the same priority be removed in the order that they are inserted, you could consider including a unique counter as the second element of the tuple to break the tie like this. Priority counter element. Now let's talk about heap efficiency of heaps. The average and worst case time complexity for inserting and extracting the minimum or maximum value from a heap, depending on the type of heap, are logarithmic. So pretty efficient, because the number of swaps required is usually proportional to the height of the heap, which is the log. The average and worst case time complexity for peak operation is constant time, a big O of 1. Peaking involves getting the minimum and maximum value depending on the type of heap without removing it. The heapify operation, where the heap is built from an unsorted list, has linear time complexity in the average and worst case. Similarly, both searching for and deleting an arbitrary element have linear average and worst case time complexity, since there are potentially requirements traversing the entire heap. And how much space do they require? The space complexity for a heap is linear, where n is the number of elements it contains. It only needs to store the elements and a small additional overhead for the list object itself. Priority queues and heaps are very important in computer science. They let you quickly find and use the most important elements from a list. This efficiency is crucial for many computer programs that perform critical real-world tasks, such as finding the fastest route on a map. Our quiz: what is the primary characteristic that distinguishes a priority queue from a standard queue or stack? Elements to be assessed by their index. It's always processed elements in the order they're inserted. It retrieves elements based on their assigned priority. It's true. It stores elements of the same data type. Following common real-world applications where a priority queue would be helpful. Scheduling tasks in an operating system where some tasks are more urgent. I think it's probably true. Managing a playlist where songs have a fixed order. Nope. Storing a list of grocery items. No. And keeping track of customer names in alphabetical order. Nope. I think 1 was our answer. What is the main reason why heaps are typically implemented as arrays in practice despite being conceptualized as trees? Arrays are always faster than any other data structure. I don't think that's true. Arrays simplify the logic for accessing parent-child nodes using mathematical formulas. I think that's probably true. And arrays allow for direct random access to any element, which is a core heap operation. Nope. And arrays are the only data structure that can guarantee to be the heap property. I don't think that's true either. That one's true. There we go. We've completed our theory, and I am a wizard. All right, up next we got our implement the shortest path algorithm. That should be fun. That's a workshop. Workshops, we know now, are a little easier than labs. They walk you through the steps. You can make an error somewhere along the way, but basically they walk you through the steps. This one has 27. And then build an adjacency list to matrix converter, lab, workshop, lab. So 1, 2, 3, 4, 5 days probably. Yep. And then we go down here to dynamic programming, which is relatively short. So we're going to come in under 100 days, but it'll probably take you 100 days if you take some time, like take a day to do your review and do your quiz. And then also, I am assuming when we get into this Python review, we're going to review all this stuff, and it's going to ask us all kinds of questions about sets and lists and classes and objects and setters and getters and all that good stuff. So we got to keep that in mind, and we haven't used some of that stuff in a while as we progress through here. So thanks for watching the video. Don't forget to comment, like, and subscribe, and I'll see you next time.